Okay, so finally I will do 2 videos for test because I had a little technical problem, but whatever, okay. So after my first video, that was a kind of introduction to this subject with the main methodological aspects of test theory, okay, we are going to see now how to build systematically, in fact, tests, okay. So let's continue the course. So I have to split my screen. So you have it now. Okay, so how to generalize this process? So what I have done previously, okay, to obtain a systematical way in order to do this and not to think, okay, to what statistic I will use, okay, what confidence or rejection region or critical region to obtain, okay, and so on and so on. We will have, in fact, a way to do this, okay, for any situation. Okay, so it's what we call likelihood ratio test. So let just me remind, in fact, key point of this, the key point that the intuition below this kind of test. So it is based on something that I have done in the previous chapter, the chapter concerning estimation. We have seen together that if I have a parameter theta, okay, and if I have the n sample of observations that depend on a known parameter theta, we have seen together that, okay, theta, so x1, xn, a sample, okay, of the density f x theta. So I write it as a density, but keep in mind that in the discrete case, it's this one, okay? The probability mass function. We have seen together that this mapping, that is the expectation of the logarithm of f capital X theta. Okay, so the expectation of the log density at the point capital X, that is the random variable having this density here. We have seen that this point, so we have seen this, that is maximal at the true value of theta. Okay, so if I want to maximize this quantity here, in fact, the maximum will be reached for the true value of the parameter. Even if I don't know it, okay, it will be, this quantity will be maximal, okay, at the true value. Okay, so keep in mind that in order to define the maximum likelihood estimator, okay, what I have done, in fact, I have approximated this one. So I have approximated this expectation and doing what? Okay, doing what I have done in the chapter concerning sampling. Okay, I approximate, it's theta here, I approximate an expectation by the sample mean based on these observations here, and I obtain here 1 over capital N, the sum from k equal to 1 to n of the logarithm of f of xi theta. Okay, so I have this, and this is what I have defined here as ln of theta. That was my log likelihood. With ln of theta, that is just, okay, what? The logarithm of what I have called the likelihood, where the likelihood is just the product from, or here it's I that I have used, so my index is I, it's not k here, I equal to 1 to n of f of xi theta. Okay, And the principle of the maximum likelihood estimator is to say that I know that the true parameter is maximal for this mapping here. I approximate this mapping for, okay, using the sample mean, okay. And what I call the maximum likelihood estimator, okay, is theta hat that maximizes okay, by the log likelihood, or equivalently the likelihood, because the log is a strictly increasing mapping. Okay, so if I maximize what I have inside or maximize the logarithm, I obtain exactly the same thing. Okay, so keep in mind that the log likelihood or the likelihood are maximal, okay, for the maximum likelihood estimator. That is an approximation of the true parameter. Okay, so in some sense, okay, I can say that up to this approximation, this classical approximation of an expectation by sample mean, okay, at the true parameter, okay, the likelihood or the log likelihood is maximal. And in fact, all we are going to do after is based on this simple idea, because, okay, I will build rejection region or critical region, okay, using this fact. That is, my log likelihood will be maximal at my true parameter. Okay, so if I have this in mind, now it won't be that complicated to do this. So let me explain the log likelihood ratio test. Okay, so I am in this situation. I have my capital N observation. I have an N sample here. I have the associated likelihood function as defined previously. That was just the product of the density taken at the xi. Okay, here I have theta. That is my parameter I want to deal with in the test process. Okay, and now we are going to do a first case. That is a basic one, just to test the fact that theta takes a particular value versus theta takes another value. So here, typically, I am in the situation where my capital theta 0, okay, is just a singleton, and where my capital 1, my capital theta 1 is just also equal to a singleton. Okay, so let me just reduce a little this in order to explain what I will do after. Okay, so H0 is the null hypothesis, that is theta equal to theta 0. Okay, and I know so that under this hypothesis, okay, under this hypothesis, so intuitively, according to what I have done before, so under this hypothesis, where we'll have ln of theta 0 will be maximal. Because, as I have said previously, okay, the point, oh, it's intuitive this, huh? The point where, okay, I can maximize, so the expectation of the logarithm that is approximated by the log likelihood is the true parameter. So if I am under this hypothesis that the true parameter is theta 0, my log likelihood will be maximal at this point. So in particular, if it is maximal at this point, it will imply that, okay, ln of theta 0, okay, will be greater than ln of theta 1 being the other parameter of interest. Okay, so under the true hypothesis, okay, I can say that ln over theta 0 divided by ln of theta 1 is big. And by big, I can say that I can write it as, okay, something that I can take greater than some number that I will denote by k. Okay? So under my hypothesis of interest, that is the null hypothesis, this ratio is big. Okay? So how to build a rejection region or a critical region? I can build it this way. I will reject if, but this one is not fulfilled, because this one is when I am under the null hypothesis. So, okay, when I am under this setting, okay, this ratio of log likelihood is big, okay? So if I want to build the test, I need to build a critical region. That is the one for which I will reject. But I will reject when I don't have this one. That is, I will reject when the ratio will be small, in the sense that it will be strictly less than k. So it is the explanation of why taking such a critical region for building my test. Okay? And you see that this test here will be built on a statistics. So our statistics of interest is what? I denote it by capital lambda of x. That is just ln of x theta 0 over ln of x theta 1. That is, okay, let me remind you, it's the product from I equal to 1 to n of f of xi theta 0 over the product from I equal to 1 to n of f of xi theta 1. Okay, so it's what we called here the likelihood, excuse me, it's what we call here the likelihood ratio statistic. Okay, and in fact I am interested on, okay, the points where this statistics is in fact less than small k, and I have here, okay, my critical region. Okay, that is, I can write it equivalently as the statistics belongs to minus infinity. Okay, so you have exactly what you need in order to build a test. And of course, in my situation here, the level is equal to what, or the size? It's the same thing. I know that alpha is defined that the supremum for theta belonging to capital theta 0, okay, of what? Of the probability under theta that delta of x is strictly less than k. But in my particular situation, in my basic example here, I have a single point inside, so it will be just probability theta 0 delta x strictly less than k. And so if I fix alpha, for example, 0.05, or in general 0 0.01, okay, then I obtain K from a table of a particular distribution, okay? And in the second step, once I have K, so now K is known and related to my level, okay? If I am interested in the power is defined as 1 minus beta in my situation. That is what the supremum for theta belonging to capital theta 1 of P theta delta X strictly less than K. And what is it? But in my situation here, it's simply because I have a single point in my capital theta 1, it will be P of theta 1 delta X strictly less than K. So you are in a situation here where if all the parameters of the test are known, that is the number of observation, theta 0, theta 1, okay, and if I am able to know the distribution of delta X, then I can do everything explicitly, okay? I can do everything explicitly. So let's see an example. And the example will be the example we have already seen together, but I want to show you that what I have done in the first video of this course is in fact just a very particular case of what we can do from a systematic way using this methodology. Okay, so let's come back to an example we have already seen. So I have x1, xn that are I, d, and mu sigma square. And here I just suppose that sigma square is known. Okay, I suppose that my sigma square is known. Okay, so I have this. I want to test H0, that is mu is equal to mu 0 versus H1, that is, okay, that is mu equal to mu 1. And here, I suppose, as I have done previously, mu 1 is strictly greater than mu 0. And I do the same remark, do mu 1 strictly less than mu 0 at home in order to practice. Okay. So I have done things in the first video of the course, okay, when I have obtained something that was in relation with the sample mean and the parameter mu 0. So let's do the job, okay, using what I have just previously introduced. I'm interested in delta of x, okay? So what is delta of x in this situation? So let me remind that it is product I equal to 1 to capital N, okay, of f of xi mu 0 over product from I equal to 1 to N of f of xi mu 1, okay? And I can obtain explicitly in my situation, because I have hypothesis concerning the distribution, I can find explicitly what is this here. So I have a Gaussian distribution, okay? So if I do this, you replace here by the Gaussian density. I keep in mind that here f of x mu is given by 1 over the square root of 2 pi sigma square exponential minus x minus mu square over 2 sigma square. Okay, so if I do the product and if I plug inside capital Xi here, I obtain the following. So I will have simplification between the 1 over the square root of 2 pi sigma square, because, okay, I have the variance that is known, I have this, so I obtain the following. So I have a product of exponential that will be the exponential of the sum. So it is exponential minus the sum from I equal to 1 to N of what? So here I have my delta x. So let's write it in a better way here. Let's write it here. My delta x is equal to what? So it's equal to this product, okay, obtained this way. So it will be exponential minus sum from I equal to 1 to capital N of xi minus mu 0 square, okay, over 2 sigma square divided by the same thing with mu1 instead of mu 0. Okay, so I obtain this. I obtain this quantity. So let's erase what I have done before, and I have now my likelihood ratio statistics, okay? The statistics of the likelihood ratio test, that is delta. I keep this in mind. So I have a ratio of exponential, so I can simplify it a little, okay? And I obtain delta of x, that is equal to what? So it will be the exponential. So I can put into factor, okay? I can put what? I can put what I want, okay? So I can do it this way. I can put 1 over 2 sigma square here to have inside here what? I will have sum from I equal to 1 to capital N of this term here where I have a plus if I make it, okay, in the numerator. So I have xi minus mu1 square minus xi minus mu0 square. So I have something like this, okay? And here, if you want, I have a bracket, okay, because I do the sum over all these differences. But here I have a classical identity, that is a square minus b square equal to a minus b, a plus b. If I use this, I obtain what? So I have this one minus this one. I have simplification between the xi. If I do this one minus this one, okay, and I obtain, so this one minus this one, that is, I obtain mu0 minus mu1, that is independent of xi, and then what I have this one plus this one, okay, this one plus this one, that is 2 xi, okay, and then so this one plus this one, I can write it this way, minus mu0 plus mu1, okay? So I can remove this one from the sum because it's something that is independent of I, and I obtain at the end exponential 1 over 2 sigma square multiplied by mu0 minus mu1. Okay, I remove here, I put this one outside, that's why I obtain it here, okay? And then I have this sum here to compute. And what I obtain, if I do this, I obtain 2 times capital M, the sample mean, because the sample mean, I remind you the definition, the sample mean is just 1 over n, the sum of the xi here. So I have 2 times the sum of the xi, that is 2n times xn over line, okay, minus, here I do n times the sum of these terms, okay, and I obtain minus n mu0 plus mu1, okay? So I have done the computation for, okay, the likelihood ratio test statistics, okay, in my situation where I have my Gaussian here, okay? So we have seen together that in this case, okay, I will build my test on the following: delta of x strictly greater than k, okay? It's my set of interest. And what is this one? In fact, I see that here, so mu1 and mu0, mu1 and sigma are and capital N are fixed parameter, okay, of my exercise. And then I see that, what can I say about this? Mu0 minus mu1, I have supposed that mu1 is strictly greater than mu0. So I have a negative exponential here, in fact, okay? And I want to maximize this one, okay? I want to maximize this one, or to make it greater than k. And to make it greater than k, in fact, since here I have a negative exponential here, that is a decreasing mapping. If I want to make this one greater than k, I will need to take xn over line, in fact, small. Okay, so this one may be written as, if I want to make this quantity greater than a particular level, I will need to take a big xn over line, because, okay, here I have a negative exponential. So I can write it this way, xn over line, greater than what? Not than k prime, but then another constant that I can denote by k tilde. Okay? So my test here is built on this area, the set where delta of capital X is strictly greater than k, that is equivalent to this one, okay? But I can also write that this quantity here, this set, may be also written in the following way as xn over line minus mu0 over sigma square root of n, greater than what? But greater than another constant, k prime. Okay, because I just subtract by mu0, I divide by sigma, and I multiply by the square root of n. So it means that my quantity of interest, in fact, is just something of this form here, something of this form. And what I obtain exactly what I have done before the break. That was in the first video. So where is it? Okay, it was here. Okay, what I have done here, RC, that is when I will reject, will be when C of X is greater than K. And what is C of X? C of X was xn over line minus mu0 over sigma multiplied by the square root of n. That is exactly what I obtain in my situation here. Okay, so see first video to see that it's what I have called Cx greater than something. Okay, and now, okay, it's finished because I just have to do, okay, how I have done before the break, that is in the first video, because I know that when mu is equal to mu0, I know that this one is a n01, so I can fix k prime in order to have a level that is, for example, 0.05. That was, okay, remind k prime equal to 1.645, okay? And then once I have this level of 0.05, okay, then I can have a look on what will be my power. That is the probability of this area here when mu is equal to mu1, and it's exactly what I have done. Okay, I repeat before the break. Okay, so you see that in the situation I have done before in the first video, at the end of the first video, given to you arguments of the fact that, okay, C of X is around 0 when mu is equal to mu0, and C of X is around a strictly positive value, okay, if mu is equal to mu1. In fact, the rejection area I obtain, okay, is just the one I obtain using, okay, the methodology I have explained here. That is the one, okay, based on the likelihood ratio test. Okay, so what I have done here as my example, it's exactly what I have done now, okay, was similar to what I have done, okay, with more intuitive arguments, okay, before the break. Okay, And so you have now, okay, a completely systematic way in order to do a test, okay, in order to test this kind of hypothesis, okay, you do the likelihood ratio test. So you have just to compute a log likelihood, okay, to see what is this area more precisely, and then to do the computation of the level and see what happened for the power. Okay, so it's some exercise that I will do in the tutorial, okay, but you have here a generic example of such a situation. Okay. And now to conclude this session, so a few remarks concerning this test, because in fact, there is a nice property concerning this test, okay, that I won't prove, okay, because I don't want to do proof. I have done enough proof in the previous session. Here in this session, we are going to admit this result that is called the Neyman-Persson theorem, okay. That is the following. So if I want to compare two tests, so here I can change a little my slide. So this one will be P theta 1. No, I can write it in fact, excuse me. So in order to compare estimators, okay, we have seen that we can compare them, okay, using their mean square error. In particular, if I want to compare two unbiased estimators, it is sufficient to compare their variances, okay? The question here is how to compare tests, okay, for the same set of hypotheses for sure, okay? So if I want to compare two tests, okay, the first thing I have to keep in mind is that I will be able only to compare tests that have the same level, okay? So I fixed the type 1 error to be equal for both sets, let's say alpha, okay, 0.05 or 0.01 in general, okay? And if this level or size is fixed, okay, then I want to be able to say if one test is better than another one. And how we are going to do? Well, very basically, because if I fix the level, okay, then I have to have a look on what is the power of the test, okay? And I know that I want this power to be big, that is my beta defined previously to be small. So in order to compare my two tests, I will compare their power, and their power in this situation is just to compute the probability under the alternative hypothesis, that is under the parameter theta 1. And so it's exactly what is written in blue on the slide here. That is, I will be able to compare, or I will say that one test is better than another one, a fixed level, if the power of this test is strictly greater than the power of the other test. Okay, so I compare in this situation the two tests, okay, for a fixed level through their power. Okay. I want, in fact, to select for a fixed level test that have the biggest power, that is the smallest type 2 error. Okay, so it's exactly what I write in this slide. And the nice and very nice property is that, in fact, if I consider my previous situation, that is this one, if I want to test theta equal to theta 0 versus theta equal to theta 1, if I build a test this way using the likelihood ratio statistics, okay, here, and then I can prove, it's what we call the Neyman-Persson lemma, that this test is in fact the best one. That is, for a fixed level, this test is the most powerful one. Okay, so in my situation, not necessary to know other way to build tests, because the one I have presented here is the best one, okay, the best you can obtain, okay? Which means that in my case with the Gaussian, okay, the best I can do, in fact, is what I have done. Okay, I can't do better in the sense of this comparison. That is, for a fixed level, it will be the one with a power that will be maximal. Okay. So now to conclude this part, okay, we are going to deal with a little bit more general situation. a little bit more general situation, but we are going to see that, okay, the principle will be exactly the same. So now I want to test, okay, more complex hypothesis. So previously, keep in mind that what I have done in the previous slide, it was, okay, previous slide, I was interested by H0, that is theta equal to theta 0, versus H1 equal to theta equal to theta 1. So I had here simple hypothesis, okay, where capital theta 0 and capital theta 1 that are just singletons, okay? Here I am in a little bit more general situation. The one where, okay, my capital theta 0 may be more than a singleton. So what we are going to test here is to test theta belongs to a set versus theta doesn't belong to the set, or equivalently, theta belongs to the complementary set, okay? So it's what I want to test in our situation. And the idea will be exactly the same as previously. Theta 0 is our hypothesis of interest, okay? So we may expect that the true parameter, the true value of theta, is inside capital theta 0. If I try to maximize the log likelihood, okay, since the true parameter has a priori to be in theta 0 here, okay, so under H0, I know that the log likelihood will be maximal for a point in theta 0. So if I consider the supremum of the likelihood on theta 0, I will obtain something that will be for sure under H0 strictly greater than the same supremum under the alternative hypothesis, that is under the fact that theta or theta 1 belongs to theta 0 complementary. So it means that under when theta 0 is fulfilled, when theta 0 is fulfilled, this ratio is big in general. And so we are going to build a rejection, a critical region or a rejection area here, saying that I will reject if this ratio is not big. That is, I will reject when this ratio will be smaller than a particular quantity. Okay? I will reject if this ratio is strictly less than a particular quantity that I have to fix. And the way I will fix it, okay, is by imposing, here you have the definition of the level here, okay, and I will obtain my K fixing my level, okay? So here the principle is the same, except on the fact that here you don't have just ln of x theta 0 over ln of x theta 1. You have to take the supremum over here for the numerator, the parameters that are related to the null hypothesis, and over the parameters related to the alternative hypothesis. Okay, but the idea is exactly the same as the previous one. Okay, and in order to fix K, I fix the level, and in general, alpha equal to 0.05 or alpha equal to 0.01. So before to do the last example of this session, okay, just let me say a few things about this test, okay? I have said that when I have simple hypothesis, okay, my methodology is perfect in the sense that the test I obtain, okay, is the best possible one, okay? In this situation, it's a little bit different. It's the objective of the last slide, okay? So for this definition, you can have a look on them, okay, but I won't need them in the tutorial. So let's just have a look on this one, okay? When I am in this situation here, the idea is how to compare tests, but the idea is always the same, okay? I said that a test is the best possible in the sense that it is uniformly the more powerful one, okay? If for a fixed size, its power function is always greater than the power function of other tests of the same size, okay? So here the idea, once again, is to compare two tests fixing a level, the level that is defined here, okay, that is the supremum of the power function on theta 0, what I have called the level here, okay. So here you have the level, so I have a fixed level here. And when I have a fixed level, okay, I will say that a test is better, or in fact uniformly more powerful, okay, if it has a power function that is always greater than the power function of any other test associated with the same size. Okay, so we have seen together that in our previous situation, in the case of simple hypothesis, we obtain such a test, okay, by the likelihood ratio test, okay. In the case where my hypotheses are a little bit more complex, that is in the case where I have composite hypothesis, okay, unfortunately, it's my remark here, in general, such a best test doesn't exist, okay, such a best test doesn't exist. So here you will have a way to find one, okay, using the likelihood ratio statistic, okay, but in general, okay, for a fixed level, it won't be possible to prove that it is better than all the other tests, okay, in this sense, a sense that is really strong, in fact, here, because, okay, I want that my power is always greater than the power of all the other tests. And in general, it's not possible to have this, okay. I may have a power that is greater for a particular region of the set of parameters, but not always in general, okay. So just keep in mind that the main difference between simple and composite hypothesis is that the methodology is totally the same, okay, in order to build likelihood ratio test, but, okay, what I obtain at the end is in one case something that is absolutely perfect, that is the best test possible for a fixed level. In the case of the composite hypothesis, okay, it's not possible to find such a test, so I obtain one, okay, and then if I want to compare with other tests, okay, but I have to compare, so I have to do the computation and see what happened, okay. I don't have a very general result in this situation, okay. So let's do an example here, and I will conclude and I will finish by this example here. So I will do the job for these situations here. Okay, so it's the concluding example of this little video here. So I am in the case where I have here n mu sigma square, okay? So I have here, okay, n sample of the n mu sigma square. And once again, we are going to consider that sigma square is fixed or is known. For example, okay, sigma square can be equal to 1. So what I have taken here in my example, so I take a general sigma square, but that is known, okay, general but known. Okay, and what I want to do here, I want to test mu equal to mu 0, okay, that is mu belongs to capital theta 0 for capital theta 0 that is just reduced to a singleton here. I have in fact a simple hypothesis here, and versus what? So in my setting H1, I don't have the choice here, okay, mu belongs to theta 0 complementary, and in this situation here, mu belongs to theta 0 complementary. It's just equivalent to say that mu is different from mu 0. Okay, so instead of comparing mu 0 with a particular order value mu 1, here I want to check, okay, it's something only related on mu 0, if, okay, I can say that H0 is rejected or not, where H0 is equal to mu 0, that I want to test with respect to the hypothesis that it is not equal to mu 0, that is different from mu 0. So how to do? But I just apply my methodology, okay, once again, so we are going to go, so there is just one point, okay, that is a little bit not technical because it's something we have already seen together, but a little bit different than what we have done previously. So I compute my statistics here. And I remind that it is what? It's the supremum for, okay, so I write the general things, okay, and we see how it adapts in my situation here over the supremum for theta belonging to theta 0 complementary of what? Of the log likelihood. Okay. And in my situation here, I am in the situation here that capital theta 0 is reduced to a point. So it is just, okay, here ln of mu 0, because I have a single point in theta 0, that is the singleton mu 0, over the supremum for mu different than mu 0 of ln of mu. And with respect to what I have done previously, the only thing I have to do here is to compute this one, because in the previous case with simple hypothesis, I have in the denominator ln of mu1. Here, I have to compute this one. But I have already done this. I have already done the job in this situation. In fact, so let's do it again, but I have already done the job. I am interested in the supremum for mu different than a particular value mu 0 of the log likelihood in the case, or here the likelihood in the case of Gaussian distribution. Okay. So what can I do? In fact, what I will do here, it's something that I have already done in finding the maximum likelihood estimator. In order to find the maximum likelihood estimator of mu sigma squared being fixed, I have maximized the log likelihood, or find the point where the likelihood is maximized, or equivalently, okay, the point where the log likelihood is maximized. Okay, so the supremum, okay, will be reached for mu star that also fulfilled. That also fulfilled what? Okay, but mu star, okay, is the point, that is what we call argmax, okay, for mu different of mu 0 of, but not the likelihood, but the log likelihood. It's the same here, because keep in mind that the logarithm is a strictly increasing mapping. So to maximize this one or to maximize with this one, I will obtain different value for the maximum, but the point where the maximum will be reached, okay, will be the same. Okay. And what happened in the Gaussian case? In the Gaussian case, I can compute ln of mu, that is just, okay, the sum from I equal to 1 to n of the log likelihood that I can compute explicitly here, because I know that f x mu is equal, I am in the Gaussian setting, okay, 2 pi sigma square exponential minus x minus mu square over 2 sigma square. Okay, so I do this computation again, but I have already done it. Okay, but whatever. I do it again, it will be just also an exercise concerning the previous chapter. So what I obtain for this one, okay, so I have the sum from I equal to 1 to n of the logarithm of this quantity here, that is just 1/2 the log of 2 pi sigma square, and then the logarithm of this one, that is minus xi minus mu over 2 sigma square. Okay, so something that I can write as n over 2, the logarithm of 2 pi sigma square. And in fact, when I will maximize in mu, I don't mind about this term that is a constant, and minus the sum from I equal to 1 to n xi minus mu square over 2 sigma square. So if I want to maximize, okay, in fact, to obtain the maximum likelihood estimator, I compute the derivative with respect to mu here, because I want to maximize, and I obtain what? So I obtain for this one 0, and here I obtain what? I obtain a 2 with a minus, because I have minus inside here, so I obtain the sum from I equal to 1 to n of 1 over sigma square xi minus mu. Okay, and this derivative is equal to 0 if and only if mu is equal to what? So the one that make this one equal to 0 is xn over line. Okay, so in fact, my supremum I want to compute here is none other than the value of the likelihood, okay, at the sample mean. Okay, and I obtain this saying that to make the supremum of the likelihood is the same than to do the supremum of the log likelihood, because log is strictly increasing. The log likelihood in the case of my Gaussian is obtained this way with a computation I have already done. I remind you, when I have computed the maximum likelihood estimator of a Gaussian in the case when the variance is known, okay, and then I obtain it, computing the derivative and proving that this derivative is 0 for this value. So if I continue, my delta of x in this situation was what? It was ln of mu 0, in fact, over the supremum over theta 0 complementary of ln of mu, but here I have seen that it was ln of xn over line. Okay, so let's see what happened for this one. It is equal to what? So here I have a product from I equal to 1 to n, okay, of what? Of I have 1 over the square root of 2 pi sigma square exponential minus xi minus mu 0 square over 2 sigma square, and over product I equal to 1 to capital N, 1 over the square root of 2 pi sigma square. And what is nice here that I will have simplification between these terms, okay, and exponential minus what? Xi minus xn over line square over 2 sigma square. And at the end, okay, I can write this. So I have a product of exponential, so I will have an exponential of a sum. And I can write it this way. Exponential, I can do it this way. 1 over 2 sigma square, okay, of what? Of the sum from I equal to 1 to n of xi minus xn over line square minus xi minus mu 0 square. I can continue my computation because I have here a square minus b square. So I obtain this one minus this one, okay, and this one plus this one. So it is exponential 1 over 2 sigma square, the sum from I equal to 1 to n, this one minus this one, and I obtain mu 0 minus xn over line, okay, multiply by what? Multiply by this one plus this one, that is 2xi, okay, so this one plus this one, so it is this one minus mu 0 minus xn over line. Okay, so I have this. I can write it this way. Exponential 1 over 2 sigma square. I can remove this one from the sum because I don't have an I here. So mu 0 minus xn over line. And what I have here, so I can develop, because here I have seen that doesn't depend on I, doesn't depend on I. So I obtain 2 times the sum of the xi that I can write as 2 times n xn over line minus n mu 0 minus n xn over line. And finally, it's something that I can write as exponential 1 over 2 sigma square mu 0 minus xn overline. And here I have 2n xn overline that simplify with this one that I'll obtain n xn overline minus n mu 0. Okay, and I can finally conclude that I obtain for this one, I obtain what? I obtain exponential minus n over 2 sigma square of xn overline minus mu 0 square. Okay, I obtained this computation in this situation. So here I have computed the likelihood ratio test statistics, okay? To obtain what? To obtain that delta of x is equal to exponential minus n over 2 sigma square xn overline minus mu 0 square, okay? And so keep in mind that I will reject in the likelihood ratio test, I will reject if delta of x is less than a particular level. But here, what do you see? You see that here you have a function of, okay, xn minus mu 0, okay? Oh, I can write it this way, it's the same. This one, okay, function, let's call it h, where h is strictly decreasing. So I have a negative exponential of this one. So I know that this one is equivalent to say that, okay, xn overline minus mu 0 square is greater than a particular level that I can call k prime, something that is equivalent to say that the absolute value of xn overline minus mu 0 is greater than k. So you have here the way to reject in this example for the likelihood ratio test, okay, testing mu equal to mu 0 versus mu different from mu 0, okay? So if I want to compute the level here, or the size, what I have to do, I have to compute, so remind you that alpha is equal to the supremum for theta belonging to theta 0 of, okay, the probability theta where I reject, okay, that is delta of x strictly less than k, that I can write as the supremum for theta belonging to theta 0 of the probability that xn overline minus mu 0 is greater than k. Okay, and here in my theta 0, I have a single point. So my level here is simply the probability for mu 0 that xn overline minus mu is greater than k. And I want to compute this probability, but I keep in mind that, once again, xn overline minus mu 0 over sigma the square root of n is under h0. This one fulfills en01. So this is simply the probability of what? The probability I have this, okay? I want to use this fact in order to compute this probability from the table of a Gaussian. Keep in mind that this probability is simply equal to the probability that xn overline minus mu 0. So I can compute it this way. Okay, so just let me want to do it in a clever way. Okay, so this probability that I can write this way, 1 minus the probability under mu 0 that xn over line minus mu 0 is strictly less than k. And what I can obtain for this term, I can obtain what? It's the probability under mu 0 that xn minus mu 0 is less than k and greater than minus k, because I have the absolute value. And this one, I can write it using this fact. I can write it that it is the probability that I have a n01 that I obtain dividing by sigma and multiplying by square root of n, that the n01 is greater than minus square root of nk over sigma and less than square root of nk over sigma. Okay. And now, okay, let's finish the computation. My alpha is equal to 1 minus the probability that the n01 is less than square root of n k over sigma greater than minus square root of n k over sigma. If I fixed alpha, I obtain alpha. Excuse me, of course, if I fixed alpha, I obtain alpha for sure, but I obtain k from the table of a n01. Okay, so it's something that I have already done. Okay, when I have computed confidence interval. Okay, when I have computed confidence interval. Okay, we have seen that, for example. Okay, and it's a little exercise to do at home. If you take alpha equal to 0.05, okay, I want to find a case that the probability that my n01 is less than the square root of n k over sigma greater than minus the square root of n k over sigma is equal to 1 minus alpha, that is 0.95. And I have already done the job for this quantity. And I know that square root of n k over sigma has to be equal to 1.96. Okay, done in chapter concerning estimation. Okay, so I have this, and now it's possible for me, okay, since if I give you all the parameters of my problem, that is the number of observation, the variance, okay, you have the possibility to find exactly the k to obtain in order to have the rejection area related to the likelihood ratio test. And if you are interested in the power function, what is the power function? It's to compute the probability mu of my rejection area, that is, okay, x n over line minus mu 0 less than my, excuse me, my rejection is right then this way. I don't know, but whatever, if I have a street or not, okay, because I am in the Gaussian setting here. So it's strictly greater than k. And in order to compute this one, so now I am in the situation where this one is no more a centered Gaussian, okay, because my parameter is mu, but what I do is this one, I can write it this way, it's 1 minus the probability that xn over line minus mu 0 is less than k greater than minus k mu. And we are going to make appear what we know when we are under mu, that is probability of mu of what? I can write it this way. So I can put mu 0 here and mu 0 here, and I will write, okay, xn minus mu over sigma the square root of n. Why I do this? Because here you have the n01 when I have mu here, the parameter of interest, and less than what I have here, it is just k plus, it's this one, okay, k plus mu 0. Okay, so I do this, then I subtract by mu, okay, k plus mu 0 minus mu, then I divide by sigma and I multiply by the square root of n, and greater than the same with a minus k here, so it is minus k plus mu 0 minus mu, this one, okay, multiply by the square root of n and divided by sigma. And so I know this one. This is n01 when the parameter, the truth, and the parameter is mu, okay, because the xi follows the n mu sigma square. So when the parameter is mu, this one is simply a standard Gaussian random variable with variance 1. And so the computation of this power function here may be in tables because all these quantities are known. This one is known from the statements. This one is the mu you want to compute, okay? Mu 0 is known from the statement, sigma is known from the statement, and the k was obtained at the previous step, that is fixing the level. So this one is a number, this one is a number, and so I have just to find in the table of Gaussian distribution, okay, what is the probability to belong to this interval from the distribution function of n0, okay? So in my example, that is in the case where I want to test this, I have obtained as a region of rejection related to the likelihood ratio test something that is not that complicated, that is this one here. I can fix the k. I can fix the k fixing the level this way, and it's a little computation I have done this one in the case of finding confidence interval for the mean of a Gaussian when the variance is known. So I obtain for k this relation in order to obtain k concretely if I want a test of level 0.05, okay, that is 5%. And then once I have fixed the level, I have my k, and so I have explicitly my region of rejection. I am able to compute now the power function, okay, just keeping in mind that, okay, doing this little computation here in order to obtain something that is n01 in order to obtain these quantities from the tables of n0. Okay, so to summarize, we have a systematic way to test hypotheses, okay, in two situations. The case of two sample hypotheses, that is theta equal to theta 0 versus theta equal to theta 1. I do the likelihood ratio test in this situation where a rejection region that is equal to delta of x less than k. Okay, I know that this test is optimal in the sense that if I fix the level, okay, it's the test that is the most powerful one in this situation here. Okay, it's a proposition that I don't have proved, but I have stated. Okay, In the case where I have hypotheses that are a little bit more complicated, that is theta belongs to capital theta 0 versus theta belongs to capital theta 0 complementary set, I can also build a likelihood ratio test that has exactly the same form, okay? Instead of taking the values of the likelihood, you take the supremum of the values over by the set of parameter of interest. Under H0, it is theta 0, capital theta 0. Under H1, it's capital theta 0 complementary. So I build my critical region, okay, my region of rejection. Then I am able to fix it completely explicitly when I fix my level, in general 0.05 or 0.01. And once I have obtained completely explicitly my critical region, I am able to compute the power function. And we have done the job, okay, completely explicitly in the case of a Gaussian distribution. Okay, so this closes, okay, the little introduction to test theory. So see you, bye-bye.